Welcome to Plutistem, and today we are covering Fajans Rule. In today's class, we'll talk about what is Fajans Rules, what are its application, why it was needed, and how it can explain various physical phenomena regarding different types of compound, especially your ionic solids. So, first thing, Fajan rules is used to explain the covalent character in ionic compounds, covalent character in ionic compounds, and ionic character in covalent compounds. Ionic character in covalent compounds. So, as per this, as per this, as per Fajan's rule, no compound is either 100% ionic or covalent. That means ionic compounds have some covalent character and covalent compound have some ionic character. So the thing is, if I talk about ionic compound have more percentage of ionic character and less percent of covalent character, while covalent compounds have less percentage of ionic character and more percentage of covalent character. And let's say at some point of time the ionic percentage becomes nearly equal to the covalent percentage, we'll say you will have a compound having coordinate bond. So if you know that, if I talk about different compounds, first thing, the problem is if I have NaCl, KCl, CSCl, RBCl, CSCl and LiCl, how can you explain since all the compounds as per LiCl, NaCl, KCl, RBCl, they should be all ionic in nature, but we found that going down the group, the solubility of these compounds keeps on increasing, and in terms of nature, these compounds are ionic in nature, but this one is completely, it has more covalent character. If all were 100% ionic, that means they should have nearly similar solubilities, but the solubilities increases down the group. So what is actually happening behind these atoms? It is explained that as per Fajan rules, the covalent character in ionic compounds, covalent character in ionic compound arises due to two factors. First, property is called as polarizing power. Polarizing power. Second one refers to polarizability. Polarizability. Polarizing power refers to how easily a cation can distort an electron cloud, while polarizability refers to how easily an anion lets the electron cloud gets distorted. These are the two primary notions that we'll be utilizing to describe the covalent character in various compounds. Ionic compound, I need to bring in a cation close to an anion. When they come close to one another, here the positive charge starts to align itself to the negative charge, and the negative charge electron cloud starts to get attracted towards the cation. Now if you see that here, the negative charge is aligning itself in this direction and the positive charge is aligning itself in the direction of anion. But we know that ionic bonds are non-directional in nature. But when the ions are coming close to one another, we find that due to electrostatic forces of attraction, their ionic cloud are now getting directional in nature. And the moment they get directional in nature, this is the property of covalent bonds. So that means the easier it is to distort the electron cloud of an anion, or how easily the cation can distort the electron cloud of an anion, based on these two properties you can explain how a certain compound is having more covalent character and why it is having less ionic character. Now, so first thing, defining everything in terms of polarizing power. Polarizing power always defined for cations. So if I want to pull the electron density from the anion, I need to have high charge density. High charged density. A higher charge density arises due to two factors. First, you should have a smaller size. A smaller size means a positive charge is more concentrated in a smaller area. So that means the anion will be more easily localized towards that cation. A smaller size. Then you should have as high charge as possible. If you have these two properties, that means you can define the polarizing power of the compound. Next, after the polarizing power, we can go for polarizability. Polarizability. How easily an ion is letting its electron cloud to get distort or move towards the side of cation. It requires again two things: size. A larger size means that the nucleus is not able to hold the electron cloud towards itself. So having a larger size means any species can easily withdraw that electron cloud from the nucleus. So a higher charge favors high polarizability in case of anions. And then charge. Higher charge means high electronic repulsions. High electronic repulsions means large size. Large size means easy distortion of the electron cloud. So using these two properties, now let's try some examples and try to explain the phenomena. LiCl, NaCl, KCl, RbCl and CsCl. Here, since the anion is same in all the given salts, so I'll only look for only the cations. Smallest size, highest polarizing power. Highest polarizing power means more covalent character. NaCl, Cl, RbCl. So here we find that the covalent character increasing, the easier for you to distort the electron cloud of an anion, higher will be the covalent character. So that means in the direction left to right, since covalent compounds are not soluble in polar solvents such as water, their solubility will be decreased in this direction, which is from right to left, or you can also say that the solubility increases from left to right hand side, because the ionic character is increasing left to right hand side, because Cs has very low polarizing power, so it cannot distort the electron cloud of the chloride ion very easily. That's why it has the lowest covalent character. Now let's switch to a different category, keeping metal same but replacing anions. NaCl, NaBr, NaI. Here, fluoride ion F minus, Cl minus chloride ion, Br minus bromide ion, NaI means iodide ion. Here, in case of NaF, F minus is one of the most smallest anions we have. Because of its very small size, it only contains only two shells and high electronegativity. That means it is most difficult to distort the electron cloud of the fluorine, because its smaller size do not permit the sodium atom to pull away its electron density. So in this case, NaF will have a stronger covalent character. That means it will have the lowest amount of solubility. And as you keep going from left to right hand side, you'll find, since the ion size is increasing, sodium can easily pull away the electron density from iodine. That's why it will have the highest solubility, because it will have lowest covalent character. Wait. Sorry. I have made it opposite. Sorry. In this case, sorry, in this case, it is most easier to distort ionic cloud for this, so it will be more covalent, while this will be ionic in nature. This will be ionic in nature, and this will be covalent because it is the most easiest to distort the electron cloud of iodide ion, and this is for your ionic. So I hope now you have understood how Fajans rule is used, how it is used to predict various trends regarding solubility of ionic solids when you switch to different types of halide ions, when you switch to different types of metal ions, and how it can be used to explain various properties of substance regarding their high boiling point, melting point, and other such properties. In case of okay, so we would like to end this lecture today here. In case of any doubt, you can add it to the comment section and we'll get back to you. Or if there's any specific topic that you want us to make the video, you can also add it to the comment section and we'll get back to you. Thank you for joining us. That's all for now.